We're going to do hydrostatic forces, which is basically measuring the total force on a plate submerged under the water. And the generic formula for it is the integral from A to B of a fixed number called delta multiplied by what's called the width times the depth and dx. And delta is the fixed number 62.5 when the units are in feet. So if the story is about 4 feet under the water, etc., you're going to use this delta. And when it is metric, you're going to use 9,800. So if it's 2 meters below the surface. So I'm going to start with a kind of overlap question just to get into the feel of things. Because these are very generic. They're just placeholders for things that contain probably x's. At least one of them will contain an x. And very often, most questions both will. So I'm going to do a very straightforward rectangle under the water story, which is kind of what we did last time. In this particular story, it's 2 meters under the water. This guy from here to here, the height is what, 3 meters? And the distance from here to here, let's have that as 10 meters. So we're being asked to find the total hydrostatic force on this thin plate of metal in this particular circumstance. So what you do is you take your shape and you randomly pick, probably somewhere near the middle, the strip. And this strip is the width. You then measure the distance from the surface to that strip, and it's going to be called the depth. I need to know what the width is equal to and what the depth is equal to, because once I know those two, I'm pretty much ready to start my integral. Now, in this story here, I am going to let the depth be called x. And the width, well, no matter where I put that strip, would you agree the width is the same thing? The width is always 10. So if you do a rectangle or a square under the water, the width will be a fixed number. But won't the depth be a little bit different? Because, you know, each strip, right, each piece of that is a little bit lower. So when you put the package together, the total hydrostatic force is the integral from a guy called A to B of delta, the width, the depth, the x. I'm going to pull delta out. The width is going to be 10, the depth is going to be x, and we have that. And now we have to figure out A and B. Now, A represents the value of x here, and that's A, and B is going to be the value of x when it's there. So what's the value of x going to be at the top of this plane?
Three.
Check again.
2.
Yeah. And what's it going to be when you get to the end of that plate? So here it's 2. What will it be by the time you get to there?
5 meters.
Right. Now, this guy delta is a big ugly number. I'm going to, for ease of calculation, just leave it alone until the end. Otherwise, I have to keep writing 9,800, 9,800, and it gets really messy. And if I add it to this thing, it just means that my values are weird. So typically, just leave that guy for a while. That's my suggestion. Now, I guess I could have pulled out the 10, but I'm not going to. Add 1 to the power, divide by the new power. Five times 5 squared, take away 5 times 2 squared. And what's that? 125, take away 20, so that's 105. Right, at some point in time, you're going to get to there, aren't you? Where you've got a number and you still haven't dealt with delta. At that point there, I would then replace the delta, in this case by 9,800. And when you multiply those two together, we'll have finished the question. It's a huge number, as a lot of these questions are. 9,800 times 105, and that ends up being 102912 zeros. In other words, 1 million and change newtons per meter squared, I think someone told us last time. And I don't really care if you don't know that or if I'm wrong. What I do know is that the answer is that. Are we comfortable with rectangles then? So I don't want to do any more rectangles, right? You stick a rectangle under the water, isn't it going to look pretty much like this question? We'll just change the numbers a little bit. Okay. So what we're going to do next? Well, we're going to do triangles underwater. And that's all we're going to do today, triangles underwater. And tomorrow, we'll probably do some more triangles underwater, and then bits of circles underwater. Now, rectangles are easy. Triangles underwater are a bit awkward. They're doable, but they're awkward. Pieces of circle underwater are absolutely ugly. Trust me, you will not like circles underwater or half circles underwater. You won't like it, but we have to do it. Well, before I even think about triangles underwater, I'm going to have to show you a skill thing called similar triangles. Because we are basically going to use similar triangles to calculate the width. So these triangles that are under the water, do you notice that if you had a triangle at the top, it's a different width than it is at the bottom, right? Because the triangle has a shape where it funnels downwards or upwards, whatever direction it's pointing. So we need to have a way of telling what the width is in terms of x. And that's where the similar triangles come in. So let me show you similar triangles. These two triangles are meant to be similar. What that means is they are the same shape, but different sizes. It's a bit like somebody took one and made an enlargement of the other. Now, if this guy is 10, this guy is, 10. No, that's a bad choice. 90. And this guy here, I'm trying to make one that's actually physically real. So that's going to be a 3-4 triangle. So that's 3, that's going to be 1200 then. All right, 120, there we go. Yeah, that's a real triangle. If you know this triangle and you want to find, say, that guy, and I tell you that this guy here is 45, we can find it because what similar triangle says is that it says this. For two triangles that are similar, corresponding sides are in equal ratio. So A and D are corresponding sides. So A divided by D is going to be the same number as the B divided by E, and it's going to be the same number as the C divided by F. So the property that similar triangles has is that the corresponding sides are in equal ratio. So if you take one side from one triangle and you divide it by the corresponding side on the other, that ratio, right, that fraction is the same number for each combination of sides. So in this question here, since I need that one, can't I say that 120 over x matches with this one? And then I can do a cross multiply, although I could simplify it. Probably should have, but too late now. And when you do cross multiply, you get that. And if you want to find x, you divide both sides by 90. And x ends up being 60.
Couldn't you just realize that 45 is half of 90 and then automatically realize that it's 60?
Yeah, but imagine it's 74 and 93.
Okay.
Right? The numbers are ugly. You really need a method. So I just picked ones because I was trying to avoid screwing up in the numbers by keeping them relatively nice. The chances are that the ratios will be nice. They'll be 2 and 3, but we're not going to deal with numbers. We're going to be dealing with x's and w's. So we need a more general version. So suppose I have a triangle that looks like this. And there's a line here. And I tell you that this guy is 12 and this guy is w. And I tell you this entire distance from here to here is 20. And I tell you that the entire distance from here to here is 5. We should be able to use similar triangles to find this fella, right? The missing w. Well, if it's not obvious who the similar triangles are, can you imagine that I separated them out? So the big triangle is 20 by 12, right? And the little triangle is 5 by w. So far, so good. Now, these two triangles are similar, right? The math tells me, or the shape tells me that I'm allowed to do this. So how about 5 over 20 equals w over 12? You probably could tell what the answer is going to be, but here we go. Cross multiply 20w is 60, and w would be 3. Okay, now let's take it one stage further. Same basic triangle. I'll make that 12 again. I'm going to make this guy x and this guy w. And I'm going to make that guy 20 again. And what I want here is, I want to find out what w is equal to in terms of x. So my little triangle looks like that. And the big triangle looks like that. So x over 20, that's those two corresponding sides, is w over 12. Now, I don't want to know, or I won't actually be able to find out what w is as a number, but shouldn't I be able to find out what w is in terms of x? Well, if you do a little cross multiply, 20w is 12x. Then won't you get w by dividing both sides by 20? And if you simplify this fraction down, I believe you get 3, what's that? 4 into that, 3/5. So what we're getting practice here is that similar triangles will allow us to get the width, because that's what w is going to represent, the width, in terms of x. So I will be able to, when I get round to doing my questions, I will be able to find what that guy is in terms of x. I will also know what the depth is in terms of x. And you see that means I now have my integral. So let's put that into effect. Here's a water line. Here is a rectangular plate, and it's designed so that the tip of it is right on the surface, right? And I'll make this 10, and I'll make this vertical distance, right? The height of the triangle, I'll make that 15, and we'll have it in meters. So I need to find what the depth is and what the width is. So randomly choose a horizontal strip about there, and that's going to be my width, which I'm going to call W. And want the depth of that strip, this distance here, then that's going to be my depth, right? And I don't know what that distance is, so I'm going to call it X. So there's my depth, it's X. What I need to know now is what W is at that particular depth. And I need to know what W is in terms of X. So this is where the similar triangles come in. I have a little X by W, and I have a big 15 by 10. And according to similar triangles, equal corresponding sides are in equal ratio. So 15W will be 10x. So W ends up being 2/3 x. The minute you know those two guys, you are ready. Oops. The hydrostatic force is the integral from A to B of delta width, depth, dx. Pull out the delta for a little while. The width is 2/3 x. The depth is x dx. Now for this story, what value of x is the top? What x gets you there? That's basically A. And what value of x gets you here? That's B.
0 and 15.
And 15. So do you see in this case, that's essentially what you would get, right? That's going to be delta, the integral from 0 to 15. I guess I could pull that 2/3 out, but it's hardly worth it. It's going to be a mess anyway. So I'm just going to leave that in situ. I think it's worth it to pull out the delta, but it's probably not that worthwhile doing anything else. So add 1 to the power and divide by the new power. Evaluated at 0 and at 15. So that's going to be 2/9 times 15 cubed, take away nothing. Okay, so 15 cubed, oops, calculator on. 15 cubed times 2 divided by 9. I'm a bit surprised. But I got 750. Did someone else do that for me? 290 15 cubed. It's just, I like it. I'm just surprised.
Yep, got the same thing.
Let me try it one more time. Okay, well, sometimes you just get a nice answer and you just have to trust it. Okay, well, in this story, isn't things in meters? So won't delta be that 9,800, which is the density of water in metric units? So we are going to go 9,800 times 750. Can you imagine in a test, if you do it this way, it's going to make my job a lot easier to check as well, because that number there's the key. So 9,800 times 750 is ridiculously big. It looks like it's 7,350 newtons per meter squared, whatever the units are. So that one triangular piece of metal, it's a big honking chunk of metal, right? It's a huge chunk of metal, but it's also got a huge hydrostatic force on it. Are we good? Right, now, I'm going to take what looks like the same question and do just one thing. And I want to show you that that does change the dynamics of how you solve it. Same triangle. It's still going to be 15 meters tall. It's still going to be 10 meters wide. But I have now moved it 4 meters under the surface. Would you agree that the hydrostatic force is now different? Right, it's lower, right? The deeper you go, don't you get more water pressure, right? But it's very similar to this one, so you would expect the math to be similar. Well, in some respects it is, and in others it's not quite the same as you might have expected. Let's do my typical strip. I'm going to call that W. And the distance from here to, oops, overshot it. The distance from here, right, the surface to the strip, that's going to be called the depth. Here's the change. I am not going to make the depth X as I did here. I'm going to make the top of the shape to the strip X. And whenever you deal with triangles, will you always make the top of the triangle to the strip, call that X. Now that does mean I have to change one thing. The depth isn't X anymore. The depth is that plus X, isn't it? So the depth changes to X add 4. Now, if you focus on this triangle, and it doesn't matter where the triangle is it not the same triangle as this one? So can I tell you that if you go through the math, the width doesn't change because of the X. Well, basically, isn't that the same picture? And so it's not really changed any. So the good news is that that doesn't change. What you have to compensate for is that the depth is now X add 4 instead of just X, right? If it's right on the surface, the depth and X are the same thing, right? The depth and where the strip is the same thing. But when you move something below the surface, this is X. The depth is a little bit different. Now you put that package together, it's the integral from A to B of delta width multiplied by depth dx. I'll pull out the delta. The width is 2/3 x. The depth is now x add 4. That's fine. Now, A and B. the value of x when you are at the tip is still 0. And the value of x when you're at the bottom, right, from top of the shape, x equals 0, to the bottom of the shape, 15. If I got that other guy handy, right. Do you see what stays the same, which is most stuff, and do you see what changes? So if you let x be from the top of the triangle to the strip, then it really doesn't matter where the triangle is. Won't the x be 0 to 15? And won't the depth be the thing that changes? On the surface? Here, agreed? Now, I won't do the whole thing. I'll take it just a little bit further and then I'll say ... That's going to be 2/3 x squared plus 8/3 x. Power rule, add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Can I just ... that, because it's really just plug and chug, isn't it? Plug and chug. Any questions? Are we good about at least this kind of triangle under the water? I won't do it, but couldn't I put this triangle 20 meters below the water? And if I did, wouldn't the only thing change would be x plus 20? Agreed? Technically, I could put some of it above the water, in which case it may be x minus 2. So I could have a little bit of it sticking above and the rest below. Right. Now, let's do a different triangle. Different in 2 ways. And the first way is, it might not be obvious, I'm making the triangle point down the way instead of the other way. Hey, how big a deal can that be? Well, you'll be surprised. Let's make this distance 3 feet. Let's make the total height of this triangle 12 feet. Let's make that distance 8 feet. So that's basically a triangle is 3 feet under the water, submerged under the water, and the triangle is 8 by 12. Right, that's what it might sound like if you said it in English. Delta is going to be 62.5 in this question because it's feet, right? So that's a imperial one. I'm going to have depth and I'm going to have width. I am going to go and take a strip and we're going to call this the width, because we always do, and width will be W. And I'm going to tell you that the distance from the top of the shape to here is going to be called X. And that makes the depth from the water surface to the same place, and that's going to be the depth. What is the depth in terms of X? What is the depth?
3.
Agreed. Can you see that little guy there is 3 and that's X? So, you know, 3 and X had 3. Now here's where things get a little bit awkward. These are similar triangles. I'm now going to draw them. The big one looks like that. And the little one looks like that. The little one's actually this piece here. Now the big one is 12 by 8. Ah, I do not have this. I know this is x, but that's not the one I want to know. I need to know that guy, right? Because that's that's this guy. What is this piece?
12 minus x.
You see where that's coming from? 12, cut out that bit. 12 minus x. Do you see it's a little bit different? A little bit messier? So orientation in a triangle can make your life a little bit more awkward. Right, similar triangles, how about 8 over w is 12 over 12 take away x. If you cross multiply, 12w is 8 times that guy. 12w is 96 take away 8x. Divide everybody by 12. Eight take away 2/3 x. I now have the width. Are you comfortable about why I had to alter this a little bit in order to get the width in terms of x? So it wasn't 12 over x, it had to be 12 over 12 take away x. Now what you're going to do next is the hydrostatic force. So it's going to be the integral of delta width, depth, dx. Pull out the delta. 8 take away 2/3 x, x add 3. Now, what is the value of x at the top of the shape? This should be coming a little bit more obvious now. At the top of the shape, x is 0. And at the bottom of the shape, x would be 12. So you imagine the width being at the top, it's right at position 0, and the width at the bottom would be at position 12. So that's going to be delta. If you FOIL this guy out, you get that guy times that guy gets you -2, that gets you 6x. You get a -2/3 x squared, and you get a +24. And at this point, I'm just going to dot it, right? Would you agree that's just a big ugly power rule with even uglier numbers? And eventually you get 412,000 or something. Thumbs up, we are good. I'm going to move this in a few moments. Anybody get any questions? Okay. Still on triangles. Would you agree triangles are a bit harder than rectangles, right? Rectangles are pretty obvious. Triangles, you get a bit more work. Here's another situation with the triangle. This time, it's a special kind of triangle. It's an isosceles triangle. And this isosceles triangle is 5 meters below the surface. And that height is 20 meters. And its width is 18 meters. And since it's metric, 9,800. And it's the usual question, total hydrostatic force. So I need to find a depth and a width. And we're ready. Start cooking. And this guy is going to be called the width, and we'll call it W. And the distance from the top of the shape to the strip, that's going to be called X. And the distance from the surface to that strip, we're going to call that the depth. Right. I'm just going to put a mute on. Okay. So where are we? Yeah. Now, I think we've probably done enough of these for this to be getting a little bit easier to figure out. Would you agree that if that distance is X and this piece up here is 5, that won't be the depth be X add 5? You agree? Now, let's build some similar triangles here. The big shape is basically 18 by 20. And the little baby shape is the bottom piece, which is W by, uh-oh, we don't know. Well, if that bit is X and the bit I want to know is actually the other piece, shouldn't we be able to figure it out like we did last time? If this is X, won't this piece be 20 take away X? Right? If this piece is X and the whole thing is 20, the piece that is left is 20 take away X. So similar triangles, corresponding sides in ratio. 18 over W is 20 over 20 take away X. Cross multiply. We get that. Distribute the 18.
But we're not using the actual side measurement.
What, the sloping side?
Yes.
Correct. Oh, I should have explained this. Not only are equal sides in corresponding ratio, but equal heights are also in corresponding ratio. So we can get away with it because of that. So I now have 360 take away 18x. Divide everybody by 20. 18. 9/10. So the width ends up being 18 subtract 19th times x. So the hydrostatic force, the integral from A to B of delta, the width times the depth dx is, oh, let's suck the delta out. The width is 18 take away 9/10 x. The depth is going to be x odd 5. Okay, where does x start and finish in this picture?
Zero and 20.
Okay, I'm going to dot this one now. Would you agree that the next few lines are foil this out to get a quadratic with some ugly fractions in it? Power rule, plug in 20, plug in 0. Huge ugly answer. Multiply it by 9,800 and get an even bigger, uglier answer. And millions are very common in these questions, so I wouldn't worry about, oh, that looks too big to be right. It probably is right. It's just very big answers. Are we good? Let's try. What else have we got to try? I think actually we're darn close. Yeah, I'll have a quick look, see if there's any others in here. I've done a triangle. Oh, I guess I haven't. At least I can set this one up. You want to do a triangle pointing that way? Let's have delta. Let's have it in feet. So we'll use that one. Let's have that 1 foot. Let's have the height, say 5 feet. Let's have the width 4 feet. Okay. There's our guy. Can I save some time and just call him W now? We all know he means width, right? This distance from the top of the shape is going to be called X. The depth is from the surface to the same place. Again, I hope it's becoming a little bit more common. Are you happy about 1 plus X is the depth? Which I call X plus 1 because it looks nicer. Now, if you want to get this fella set up, the little baby triangle has a height of X and a width of W, and the big massive triangle has a height of 5 and a width of 4. So X over 4 is equal to W over 5. Cross multiply and divide by 4. In fact, isn't that one easier to do than the other one? Because the numbers that you're going, or the letters and numbers you're going to use don't really need to get altered. They're pretty much
Isn't
what you
it
see.
X over 5?
Is it X over 5? Did I screw up? X over 5, W over 4. Thank you. X over 5, W over 4. Let's do it again. I'm not sure what I did there. 4x, 5w, 4/5. Okay. Very similar looking answer, but the other way around. Right. Put this package together. It's going to be the integral from the start of the shape 0 to the bottom of the shape 5. Delta. These two multiply together. So that's going to be 4/5 x times x add 1 dx. And yeah, dot, dot, dot. So if I give you a triangle, isosceles right angled, and I give you it pointing up the way or pointing down the way, do you feel comfortable about getting the hydrostatic force?